All right, welcome back. Today, we're going to dive into a real workhorse of power electronics, the three-phase bridge rectifier. If you're in an electrical engineering program, you already know this circuit is absolutely fundamental. We're going to break down not just how it works, but more importantly, why it is the undisputed champion for heavy-duty power conversion.
So here's our game plan. First, we'll set the stage with the core challenge that industries face. Then we'll get our hands dirty and dissect the rectifier itself. After that, we'll get into the fun stuff, the math, to model the current, and then put our theory to the test with a real-world case study. And finally, we'll answer that big question. Why is this the circuit you see everywhere in high-power applications?
Okay, first things first. Before we can really appreciate this elegant solution, we've got to understand the problem it was designed to solve, and that is a fundamental power challenge that you'll find in almost any industrial setting.
I mean, just look at this beast. Big industrial motors, heavy-duty welding gear, things like that. They are thirsty for massive amounts of stable, direct current. That's DC power. But here's the catch. Our electrical grid, the power coming out of the wall, it delivers alternating current, or AC. And that mismatch, right there, is the core engineering problem we need to fix. So how do we bridge that gap between AC from the grid and the DC our machines need? Well, engineers came up with a beautifully simple and incredibly tough solution, the three-phase, six-pulse bridge rectifier. Let's really break down what we're looking at here. Over on the left, that's our three-phase AC supply. In the middle, that's the heart of the whole operation, the six-pulse diode bridge. And over on the right, that's our industrial load. It's got resistance, a big smoothing inductor, and that DC voltage source. Now that DC source is really important. It often represents what we call back EMF, which is basically the voltage a spinning motor generates on its own that our rectifier has to push against. So you can think of this entire circuit as a kind of powered translator. It's taking those three wavy, oscillating AC voltages and skillfully converting them into a powerful, much steadier DC output. And I have to say, that inductor, L, is the real unsung hero here. Its whole job is to fight against changes in current, and that's what really smooths out the DC and keeps it flowing continuously. All right, now for my favorite part, let's get into the mathematics. And don't just think of these as equations. This is the language of engineering. It's how we can precisely describe and even predict exactly what's going to happen in this circuit.
You know, all complex analysis starts from a simple, fundamental principle. In our case, it's Kirchhoff's voltage law. When we apply it to our circuit, we get this: the governing differential equation. This is the blueprint. It perfectly describes how our input voltage is going to drive the current through our specific RL load. It's the key to everything. And if you solve that differential equation, you get this beautiful result. This is the general solution for the current, and you can literally see it's made of three distinct pieces. You've got your steady-state AC part, driven by the source. Then there's a transient part, which fades away after you first turn the machine on. And finally, there's a DC offset, which is there because of that back EMF in our load. Now, in the real world, what we usually care about is how the circuit behaves once it's been running for a while. We call that steady state. And we can find that solution with one simple logical condition. The current has to be continuous. Where one 60-degree pulse ends, the next one must begin at the exact same current level. Once we apply that little bit of logic, boom, we get this powerful final equation that lets us predict the output current with incredible precision. Okay, pay close attention here because this is a really critical design concept. Does the current stay flowing continuously, or does it sputter out and drop to zero between pulses? Well, that all depends on the load itself, specifically its impedance angle. As you can see on this graph, if your load is inductive enough, you stay in that nice blue region of continuous conduction. And for things like smooth motor operation, that's almost always where you want to be. All right, so that's the theory, lots of equations, but does it actually work in practice? Let's put it to the test. We're going to apply everything we just learned to a real-world case study and see just how good our model really is. So we're going to walk through this step by step. We'll start with the setup, then we'll crunch the numbers using our equation. After that, we'll take a look at what it means for the components, like the diodes. And finally, we'll zoom out and look at the whole system's efficiency. So here's our scenario. We've got a standard 208-volt line-to-line input running at 60 hertz. It's feeding a load with 2.5 ohms of resistance, 1.5 millihenries of inductance,
and a 10-volt DC back EMF. This is a very, very typical industrial setup. Okay, time to do the math. We take all these numbers and we plug them right into that big steady-state equation we derived earlier. We run the numbers and what do we get? Our model predicts an average DC output current of 105.77 amps. And yes, that is a ton of current. But here's the million-dollar question. Is our calculation right? This is the moment of truth. On the left, you've got our value from pen and paper. On the right, you've got the result from a powerful PSpice computer simulation of the exact same circuit. And just look at that. The simulation shows the current settling right around 104.89 amps. I mean, they are incredibly close.
So what's the big takeaway here? It's simple, really. Our math works. The model is remarkably accurate. We're talking about a difference of less than 1% between our hand calculation and a sophisticated computer program. That tells us we can absolutely trust our analytical approach.
So, we've done the theory, we've done the math, and we've proven it with a simulation. All of this brings us to our grand finale, and maybe the most important question of all. Why this circuit? Why is the three-phase bridge rectifier the undisputed king of high-power applications? Well, this table really says it all. When you put it head-to-head with a single-phase bridge, it's not even a fair fight. Three-phase can deliver way more power. We're talking megawatts. Its output is naturally much smoother, with a ripple frequency 6 times the source, which means less filtering is needed. And it's more efficient. It has a higher power factor, so it draws energy from the grid more gracefully. So let's boil all of this down to the 3 main things you absolutely need to remember. 1, that inductor is your best friend. It is absolutely critical for maintaining a smooth, continuous current. 2, a big inductor doesn't just smooth the output, it also helps improve the shape of the current being pulled from the grid. And 3, for any serious industrial job, anything over 50 kilowatts or so, 3-phase isn't just an option, it's the professional standard for very good reasons. So we've pretty much mastered the ideal rectifier, but that leaves us with one final nagging question. Our entire analysis assumed a perfect AC voltage source. But what happens in the real world, where the power grid itself has inductance? How do those imperfections mess with our perfect model? Well, that's a fantastic question, and it's exactly where we're going to pick things up next time.